Welcome to the last lecture in this class. Wow, you finally made it till the very end. Congratulations. You have come so far. You've learned so much and picked up so many new tool sets that will allow you to solve problems in science and engineering using applied and analytical mathematics. From the easiest problem of a linear first-order ODE all the way to a complicated, diffusing, semi-infinite boundary partial differential equation. And we've learned a lot about how energy and material and mass diffuses into different systems in different dimensions, different geometries, different coordinate systems. And there's one last problem or class of systems that I wanted to cover today. And this class of problem is especially important for my discipline of chemical engineering, but actually more broadly in a variety of science and engineering systems. And that problem is a problem that not only involves diffusion, but also a chemical reaction inside that system. So today we're going to focus on a diffusion reaction system. Suppose we have a spherical catalyst. It's a small pellet that is able to undergo a chemical reaction inside the substrate. This spherical catalyst of dimensions R0, that's the size of the catalyst, is submerged inside a bath of reactants. I'm going to call it A, species A. So you've taken a bunch of catalysts, put it inside of a beaker containing a solution, and a solution inside the bulk has a reactant, A, at concentration Ca infinity. So that's the bulk concentration of the reactant inside your beaker being sloshed around by a stir bar. And this reactant A is going to diffuse inside your spherical catalyst because the catalyst is a porous material. It is porous, which allows species A to penetrate into your catalyst from the exterior. And as it penetrates into the catalyst, there is a chemical reaction of reactants going to products. In this particular case, we've chosen a simple first-order irreversible chemical reaction that looks like the following. So there's this chemical reaction happening inside this spherical catalyst. So we want to figure out, what does the concentration of the reactant look like inside this catalyst? So the goal is to optimize catalysis and reaction engineering by designing the world's most perfect spherical catalyst that will carry out the chemical reaction that you want because you want the product B. You're an engineer, you're working at a company, and you want to maximize your profit by having as much product B as possible. So then you as an engineer is tasked with the objective of, how do I design the right kind of catalyst that contains the right chemistry, but also the right material science, the right porosity, the right rigidity, the right transport characteristic that allows the reactant to diffuse easily inside this catalyst while not interfering with the chemistry. That seems like a very useful applied problem. And we're going to work out this problem to figure out, how should we design this catalyst. Now first, let's make some considerations about the rate law inside this catalyst. For a first-order irreversible chemical reaction, the rate of generation of the reactant A looks like the following. And I said the rate of generation because the sign convention of this expression is such that we have a negative generation, in other words, consumption. So A is being consumed at a rate that's proportional to its concentration, Ca, that locally changes inside this catalyst, and a prefactor, which is called the rate constant. And the rate constant depends on temperature. It might be an Arrhenius relationship. And that's chemistry. So how good of a chemist you are will dictate how good your rate constant K is, how strong it is. All right. For this problem, where we have a spherical catalyst, the best coordinate system to use is spherical polar coordinates, with some radial vector r pointing outwards from the origin of the catalyst. So the scalar coordinate r tells you how far you are away from the origin at a particular distance r. And in spherical polar coordinates, there's also the angle theta that tells you how far you are away from the North Pole at a particular point inside the catalyst. And also the other angle phi that tells you where you are laterally along the direction that is a cross-section along the equator. So those are the three independent coordinates that describe this sphere in spherical polar coordinates. Let's write down the governing equation for this system. A couple of weeks ago, we derived the basic equations in transport. One of those equations were a mass balance conserving species mass inside a system. And in that equation, we had accumulation of a chemical species, in this case, a reactant, is equal to the diffusion of species inside that system. So these two terms over here on the left would correspond to the heat equation or the diffusion equation. But we have one extra term here called the generation, which tells you how much of that species is being generated inside that system. And in this particular case, A is a reactant, and therefore we have a negative generation. So A is being consumed inside this case. Okay, so in general, what we find here is that the chemical concentration Ca is a function of r, phi, theta, and time. So it's a four-dimensional problem. Just like that. So Ca depends on r, theta, phi, and time. Now, if you think about the system, we're throwing in a bunch of catalysts, these spherical pellets inside of a beaker. It's well mixed, and therefore the bulk concentration of reactants inside your solution would expect to be homogeneous, uniform distribution inside the whole beaker. So around the spherical catalyst, there is equal concentration, Ca infinity, all the way around this catalyst, over in theta, also in phi. So North Pole, South Pole, along the equator, everywhere, no matter which direction you look, the concentration at the surface is all going to be equal to the bulk concentration Ca infinity. So then, if you were to go to a particular distance in r, say along the North Pole, at this point right here, if you were to measure the concentration at that point, and then keep the equal distance but go all the way to the South Pole, right around there, then you would expect those 2 points to have the identical concentration. Along that shell of a particular radial distance, you would expect that the catalyst wouldn't really care which angle I'm at. As long as I'm along that fixed radial distance, the concentration of my solute, of my reactant, will be the same. Therefore, the solution, you would expect it to be symmetric about the angles theta and phi. In other words, there is no dependence of theta and phi on the overall concentration. Therefore, for this particular problem, we're making a physical assumption and an approximation that the concentration is only a function of how far you are away from the origin and time. Therefore, this Laplacian operator inside this diffusion term only requires the radial component. And then once you have the radial component, you'd have something that is identical to the diffusion equation plus the first order chemical reaction, negative K times Ca, that would go into this generation term. And that would be your overall governing equation. Now, let's consider today the situation where there is no transient dependence on the concentration profile. So the way in which you would have a time-varying concentration would be a situation like a startup of a chemical reactor. If I were to have a big tank of a reactor, I pack it with a bunch of catalysts, and initially, as I start to flow reactants into the solution, I'll have a transient startup period that'll adjust and slowly go towards steady state. But in most applications, your reactor is running continuously for a very, very, very long time. In effect, it's running at steady state. You put your reactor, this huge tank, there's initial transient, and there is an importance of how to do that transient carefully, but the ideal case is the transient would die away, and you'd run it at steady state at a fixed situation for a very, very long time to maximize your output. So let's first consider the case where you're running all the way at steady state, where the transients have died away, and you only care about the steady state operation. Because as an engineer, you want to ultimately maximize steady state profit. Of course, if you're really a chemical engineer, you have to think about disturbances and noise, and you have to think about feedback and control. What if the temperature fluctuates outside? What if the exothermic reaction causes the temperature to run away? Then you have to add a heat jacket, you have to apply a controller. Okay, in those cases, sure, you need a transient term because feedback is automatically going to be dynamic, time varying. Noise is often time varying, and therefore you'd have to account for this accumulation term. But let's do the ideal case. Ideal case, steady state operation, no noise on the outside. So in that case, concentration, Ca, will only be a function of radial distance r, no more time dependence. So in essence, it turns into an ODE. Let's write that down. All right, just a steady state solution. So the left-hand side set to 0, I divide it through by the diffusion coefficient of the reactant going into the catalyst. Now, we now know what the Laplacian operator looks like for only the r component of spherical polar coordinates. It looks like this. Spherical polar coordinates. The Jacobian gets added here. So the Laplacian in spherical polar coordinates has the usual Cartesian component that looks like the first term. The second term accounts for the curvature from the Jacobian. As you go out, you have a shell that gets bigger and bigger, and therefore you have a Jacobian term right here. And lastly, I've taken the reaction term straight down. Let's call this ratio of the rate of reaction over the diffusion of the reactant equal to some constant a squared. That's just purely for convenience. Now I'm going to do one more step, which is to multiply the entire equation by r squared. It looks something like this. I'm now using the shorthand notation where I'm putting primes instead of the derivative. And therefore, we have r squared Ca double prime plus 2r Ca prime minus a squared r squared Ca. Okay, so have you seen an ODE that looks something like this that we've learned throughout the course? It kind of looks like this one. This equation right here. This one I'm hoping you've seen before in this class. This is the Bessel's ODE. But if you look very closely, there's a couple of differences. First, there is no factor of 2 for this curvature term. Secondly, over here we see a plus, and in our equation we see a minus. So there's actually some differences, and therefore we don't have a Bessel's ODE. Remember, we're using spherical coordinates because of a spherical geometry. We're not going to get the cylindrical Bessel's equation or the cylindrical Bessel's function as solutions to a spherical geometry. Not generally. Well, you're going to see a little bit later that there's a different type of Bessel's function called the modified spherical Bessel's function, which is what we have instead. But what's so interesting about spherical polar coordinates is that you can make a clever substitution and rearrange this equation into an equation that's much easier to solve. So let's do a little math trick. We're going to make a clever substitution by letting the concentration of A at some position r equal to a new function u, which is only a function of r, divided by r. It's just a clever substitution. And what it actually does under the hood is it's pulling out this Jacobian, because as you go further and further away for a sphere, you have a Jacobian that you can account for. And so now when you take this form and basically swap all of your CAs with u instead, I can obtain an ODE for u instead of C sub a. Now, it's a little bit cumbersome algebraically, because you need to take a couple of derivatives. You need to take CA prime for this curvature term. You need to take CA double prime for this normal diffusion term. So then you're going to have to do the product rule, and it gets a little bit grungy. And you substitute this into the original ODE, and you massage it, do a bunch of algebra, and then out comes this equation at the end. So after substituting this form into the ODE right here, and you do a bunch of algebra, a bunch of terms are going to cancel. In fact, the curvature term is exactly going to cancel. And you're going to end up with the following ODE. U double prime minus a squared u is equal to 0. A linear, constant coefficient, second order ODE. So that's pretty cool. You went from non-constant coefficient ODE to a constant coefficient ODE, which we can solve very easily. Find the characteristic equation, and then you find your roots, which in this case is plus or minus a. So you have real, distinct roots, and your solutions are exponentials, or cinches and coches. I'm going to choose cinches and coches for convenience. Just like that. So we have u of r is just a cosh ar plus b cinch ar. Now, this is our solution for u, but what we want is concentration of A. Therefore, we just have to divide by R, and we get our solution. There we have it. So each of the coches and cinches just divided by R. Now, it turns out this solution right here is called the modified spherical Bessel's function of the first and second kind. It's extremely long. I'm going to say it again. Modified spherical Bessel's function of the first and second kind. And the modified part comes because there's a negative sign in front of this a squared r squared ca term. You'll get the normal, or just spherical Bessel's function, which are sines ar divided by r, cosine ar divided by r. So the orthogonal function analogous version of cinches and coches, if you were to have a plus here. So plus sign here gives you the spherical Bessel's functions of the first and second kind, cosine over r, sine over r. And there is also the modified cylindrical Bessel's function if you were to switch this over to a negative. So it actually is exactly analogous to Cartesian rectangular coordinates. You get cinches and coches if you have negative sign here, and you get sines and cosines if you were to have a positive sign here. And it's the same thing for cylindrical coordinates and spherical coordinates. So it's no big deal. We just have a solution. It's just so funny that in spherical coordinates, you can use this little clever substitution, convert this ugly ODE into a simple Cartesian-looking ODE, and then account for that Jacobian by dividing by r. It's so fascinating that in cylindrical coordinates, which is usually living, a lot of times you're solving a 2D problem in R, because that R lives along a plane in cylindrical coordinates. Whereas in this case, the R points along a 3D space. So in the cylindrical coordinate system, the R scans along a two-dimensional sheet or plane. And therefore, when you solve what's called the Laplace's PDE in that problem, you get log R's to come out. And log R's kind of kill you at the origin, but also infinitely far away. Whereas for spherical coordinates, the Laplace's equation gives you a 1 over r solution. And that's why you can easily tack this on and work out problems fine in 3D. But the log r ends up killing us a lot of times in 2D. So that's why Nobel Prize a couple of years ago in physics was 2D materials. It's the properties of two-dimensional materials behave so differently from 3D. And there's hexatic crystalline phases in 2D that you don't get in 3D. So 2D and 3D world are completely different physics. And it's got really interesting math that goes along with it. Okay, let's keep going. If none of that made sense, forget about it. Let's just keep going. We have this solution so far. Oh, but we need boundary conditions. We haven't really considered boundary conditions in this problem yet. Let's think about that. So, one of the boundary conditions is extremely easy to determine because I already told you what it is. On the surface of the pellet at R0, along the surface, it's equal to the concentration in the bulk Ca infinity. Now, technically, as you take upper division chemical engineering classes and your classes on heterogeneous catalysis, you will learn that the bulk concentration of your reactants inside your beaker is not necessarily going to be equal to the surface concentration right near your catalyst pellet, because you're going to have boundary layers external to the pellet, and there is a coupled diffusion reaction problem that you have to work out because the concentration will drop when you get closer and closer to the pellet. But we're going to ignore that because there's a stirring rod in there. It's infinitely mixed. It's a high Reynolds, high Peclet number problem, and therefore the concentration infinitely far away is equal to the concentration right up to the surface. You're going to learn all these things in your later classes in chemical engineering, but for now, simple case. We're given the bulk concentration right at the surface. Let's write that boundary condition down. Just like that. Well, we now need a boundary condition where? Usually for Cartesian coordinate geometries, you did this boundary condition at x equal to 0, x equal to L, and you had some kind of Dirichlet-Neumann-Robin boundary condition at both ends. With spherical polar coordinates, it's actually similar to cylindrical coordinates. We need to apply a symmetry boundary condition, or equivalently, that the concentration must be finite at the origin. Like I said, this is analogous to the slope or the derivative of the concentration at r equal to 0 being 0. You can just see this by taking the derivative of both sides. You can clearly see that the slope of the concentration profile right at the origin must be equal to 0. And that's called a symmetry boundary condition. Because let's make a counter argument. Let's suppose that the derivative of the concentration were not equal to 0 at the origin. Your concentration profile would look something like this. You'll have a concentration Ca infinity out here, and as soon as it comes to your surface, it's going to start reacting away. And then if it weren't constant right at the origin, you would get a slope that causes the concentration to start fluxing into your origin. And because it's symmetric about the origin, you're going to have another equal profile on the other end that looks something like this. And therefore, what you have is a concentration of reactants that will accumulate right at the origin. And it physically means that you have fixed first law. You have negative d grad Ca fluxing into your origin. That would be crazy, because what that's saying is you're going to have more and more accumulation of reactants at the origin, and your concentration is going to diverge to infinity because you're cramming more and more solute, more and more mass into a singular point in space. You're packing, you're fluxing mass into the origin, and therefore your concentration would be infinite. It would not be finite. So therefore, to prevent that from happening, you enforced that the slope must be equal to 0. So your concentration derivative here has to be such a way that your slope right along the origin is 0. And that ensures that there's no flux of reactants at your origin, which is equivalent to saying your concentration must be finite. Okay, so let's consider the second boundary condition first, because it's going to help us eliminate one of these constants of integration. Let's think about cosh of 0 divided by 0 and sinh of 0 divided by 0. you have to use L'Hopital and take the limit because now we're having situations of 0 over 0 sometimes. So let's first plot what cosh and sinh looks like. All right, so cosh at 0 goes to a finite value of 1 because cosh is the sum of the exponentials plus and minus divided by 2. So at 0, you get 1 plus 1 divided by 2, which is 1. So cosh of an argument of 0 goes to 1. And so the numerator goes to 1, whereas the denominator at r equal to 0 goes to 0. Therefore, the sum, the ratio of these two things goes to infinity. So we know that cosh 0 over 0 diverges to infinity, which would mean that the concentration's diverging out to infinity. This other term over here, sinh, is the more interesting one, where at the origin, it goes to 0. So this is a situation where you have 0 over 0. If you use L'Hopital's rule, this becomes a finite number, similar to sine 0 over 0, which also goes to a finite number. Therefore, what we have is this term is finite, whereas this term over here goes to infinity, and therefore you need to kill off this term. You need to make sure that this term dies, and the only way to do that is to set a equal to 0. So this boundary condition tells us that a must be equal to 0. And therefore, we obtain one of the constants of integration. All we have left is b sinh ar divided by r. We can use the other boundary condition, number 1, to obtain the constant b. It looks like this. Just like that. And we're done. We have the full solution. Let's write it down cleanly. And we have our final solution. Ca, which only varies with the radial distance outside your catalyst pellet, normalized by the surface concentration, is equal to r0 divided by r sinh ar divided by sinh a r0. And remember that this parameter a is equal to the square root of the reaction rate constant k divided by the diffusion coefficient of your reactant inside your pellet. Now, I wanted to plot this for different values of a. And a has a very important physical significance to it. A physically is a ratio of how strong your reaction rate is divided by how fast your transport is. How quickly is the reactant penetrating through the porous material on the denominator, and how good is your reaction rate on the top. So grossly simplifying things, this is kind of like how good is your chemistry? That's your numerator. If your chemistry is very good, then your rate constant's very good because all the A's are being converted into B's infinitely quickly. And on the denominator, that's like how good your material science is. If your material science is really good, that means that your rate of transport is very good because your diffusivity is so large that all the A's can penetrate into the catalyst extremely quickly. Therefore, this is a ratio of how good your chemistry is versus how good your material science is. So with that in mind, let's plot this for different values of this competition. Let's try plotting the concentration inside the pellet. So here is the radial distance from the origin going outward. So just to be clear, we're doing the internal problem. We're inside the catalyst pellet. We have a radial distance r going out from the origin to the surface. Now the surface concentration is fixed at A infinity, so Ca infinity. That's the value that we must go to at this point. So beyond that value, it's going to be flat at Ca infinity because we're now outside the catalyst. This is the bulk solution. And the concentration's fixed at Ca infinity outside. It's internal. This is where all the chemistry is taking place. Now, let's do the two limiting cases. Let's consider the situation where the reaction rate constant, K, is extremely large. So you are an amazing chemist. You developed an amazing chemistry such that the rate law is very large compared to your lousy material science, slow diffusion. So K is much, much bigger than D. under these situations, you would expect the reactant to touch the surface of the catalyst and immediately react completely away a couple of nanometers into your catalyst. Because your reaction's so good. As soon as it touches the surface, boom, it's all become reactant to product B. Therefore, your concentration profile of A would look something like this. Just like that. So your reactant concentration will suddenly drop to 0 and then stays at 0 all the way. And there'd be a very, very small boundary layer right here where all the action's taking place. Your reaction is so good that you're actually wasting all this room where no chemistry is happening. Your material science sucks so bad that you're wasting all this space. And that's a bad thing as an engineer, because you wouldn't want to develop this precious platinum catalyst that's really expensive, or gold catalyst, really expensive, and you're going to pack this into a 10-meter reactor, and you're telling me that you're going to waste 95% of your material where it's not doing any chemistry? Get out of here. You're wasting the company's money. So you wouldn't want the situation. Again, that's a balance that you have to strike as an engineer. You wouldn't want to develop a catalyst like this where your reaction is so good, but you're wasting all this space. That wouldn't be good. Just make a smaller catalyst so that your catalyst is a little smaller, and you can then increase the surface area and pack even more smaller pellets inside your reactor. Again, these are the kinds of considerations you can make by knowing the solution to this equation, and you can advise people based on this ratio of reaction rate to transport. Now, let's suppose the other extreme. If your transport is amazing, you are an incredible material scientist, you've developed the newest porous zeolite catalyst that allows rapid transport. The pores are so well designed that the reactants could jet right through and cut through this catalyst, and the porosity is so well tuned. Whereas your chemistry is lousy and your chemistry sucks. In that particular case, you would expect that your reactant would just cut all the way through your concentration field. It would look something like this. Just like that. That's what I drew in pink right here, is the case where your reaction rate, your chemistry, is much, much weaker than your diffusion coefficient. Your reactants are going to penetrate all the way through, and it's going to make it all the way to the core of the reactor. Now, again, it all depends on what you are looking for and what you and your company are looking for in terms of what you want to achieve inside this catalyst. In this case, you're actually achieving a large rate of reaction because your surface of reaction is the area under this curve. So the area under this pink curve is going to be your total reaction, rate of reaction inside this catalyst. But if your rate constant is so small, then the actual rate of which you're producing products is actually pretty small. So even though you're effectively utilizing all of your catalyst, your chemistry sucks so much that you're actually not producing a lot of products. And that may also not be a good situation. And so obviously, you're going to want to strike a balance between how good your reaction rate is versus how good your transport rate is. So you're going to get a family of curves inside this range from K much, much less than D, which is this pink curve, to K much, much bigger than D, which is this blue curve very close to the boundary. And you're going to get an entire family of curves. That looks something like this. And once again, notice that the boundary conditions are always obeyed. At R equal to R naught, the surface concentration is always fixed at R CA infinity, and along the origin, we always have zero flux. There's no flux of chemical species of reactants accumulating at the origin. And if you were to plot this solution for different values of A, you would find exactly this family of curves for different values of A. All right, that is all I wanted to cover with diffusion reaction systems. And in fact, in my graduate class, I dig deeper into this problem and do what's called a perturbation analysis. A perturbation analysis is a very cool mathematical tool that allows us to probe the limits of fast reaction or fast transport. And in chemical engineering, there's a very famous non-dimensional number called the Thiele modulus, which is the non-dimensional version of this. You just basically put your R0 inside this A, and you non-dimensionalize it, and you get a Thiele modulus. And you can do an expansion of our equation for small and large values of this Thiele modulus. And you can figure out the limits of both of these cases and do an expansion. And it turns out to give you a lot of really, really useful insights, in particular about the concept of scaling. And scaling is one of the most important subjects in my mind with engineering. If you make the reactor twice as big, what happens to your output? When you make the polymer molecular weight go from 10 to 100, what happens to your dynamics, the viscosity, the rate of reaction, the brittleness, ductility? This scaling concept is an extremely powerful tool that we use as an engineer. All right. Good, that is everything I wanted to cover related to diffusion reaction. And I'll have a bonus track after this, but otherwise, this is all I wanted to cover in terms of scientific content in this class of applied mathematics in science and engineering. Best of luck in the rest of your studies, and I will see you later. Bye.